A quantum network just learned how to recognize entanglement, even when part of the signal disappears. This is Global Tech Pulse. Most quantum systems today depend on something called GHZ entanglement. In a GHZ state, every photon behaves like a perfectly synchronized chain. One photon changes, the entire system changes. One photon disappears, the entanglement collapses completely. W states work differently. Instead of logging information into one exact photon arrangement, the quantum excitation spreads across multiple photons at the same time. The system no longer says the photon is here, it says the possibility of photon spreads across all locations simultaneously. That shared probability structure makes W states far more resistant to loss. Even if one photon disappears, the remaining photons still preserve most part of the entanglement, but that created a massive measurement problem. Older detectors could not clearly separate a real W state from partially organized quantum noise. The signatures overlapped. Researchers had to reconstruct the quantum state indirectly using thousands of repeated measurements and massive post processing calculations. The new system changes the measurement architecture itself. Researchers built an optical network filled with beam splitters and phase controlled pathways. As photons enter the network, each one is split into multiple possible paths at the same time. These paths are carefully time aligned so the waves overlap again inside the device. Now, the key mechanism happens during that recombination. The overlapping probability amplitudes interfere with each other. Some path combinations reinforce each other, increasing detection probability at specific outputs. Other combinations cancel completely through phase mismatch. If the incoming photons truly share W state structure, their interference pattern logs into one very specific symmetry. That symmetry survives the cancellation process and appears as a stable detector signature. So the detector is not tracking individual photons. It is testing whether the entire multiphoton system forms a self-consistent interference geometry within the group. Instead of rebuilding the quantum state afterwards, the system directly projects the incoming light onto W state pattern and checks if it matches. But this only works if the photon arrives almost perfectly together. Even tiny time drift destroys the interference effect. The researchers stabilized optical path lengths and synchronization down to femtosecond timing windows, preserving coherence long enough for reliable detection. That matters because future quantum networks will operate in noisy environments. The particles constantly disappear or scatter. GHZ systems fail catastrophically under loss. W states degrade gradually. That makes them far better candidates for distributed quantum internet routing, quantum repeaters, and fault-tolerant photonic computing. And for the first time, researchers can now directly verify those resilient entangled states in real time. Global Tech Pulse. If you want this to be explained in an elaborate video, comment W state because most of us are being fed with misconceptions about quantum entanglement as a mystery than a realistic quantum experiment. Subscribe and comment your queries. Let's innovate to sustain. Nandri, Vanakkam.